The first step in memory encoding is establishing working memory. But working memory is very limited in its capacity. You can quickly become overloaded with working memory. The working memory can only hold 4 to 7 new pieces of information. That is very limited. What is worse is that the working memory does not last long. It doesn't even last a minute. In 30 seconds, you can lose this information if you don't rehearse it. The biggest enemy of working memory is distraction. So our distractions come in the form of cell phones. So when there is cell phone distraction, the cell phone is competing for those 4 to 7 pieces of information and you quickly go into overload. We call this overload cognitive overload. And cognitive overload is the enemy of working memory. So we don't want distraction, we don't want cognitive overload, and because these negatively impact working memory, and you will spend a lot more time to learn something very simple. Therefore, multitasking is an absolute no-no when learning new information. So now let's take a look at how we rehearse the information that we have just been exposed to so that our neural pathway will become stronger. So we have the action potential arriving at the synaptic knob. This causes voltage-gated calcium channels to open, and calcium rushes in. Calcium then causes exocytosis of the synaptic vesicles, which release the neurotransmitter into the synaptic cleft. They diffuse across and bind to neurotransmitter receptors on the postsynaptic neuron. Once they bind to this, ligand-gated sodium channels open and sodium rushes in, bringing positive charges into the postsynaptic neuron. The postsynaptic neuron is then depolarized and an EPSP is created. So in this way, the neurons all along the neural pathway become excited and the information is rehearsed many, many times. We call this process tetanic stimulation. Tetanic stimulation means repeatedly going through the same process and activating neurons all along the pathway so that a strong memory may be laid down. So you have rehearsed your new information. You have studied your concepts many times. There is one more way that you can hack the learning process to your advantage, and that is to review your material within the first few hours of completing your previous study session. So when you hit your books again within the next 4 to 6 hours, you can take advantage of the calcium that has been accumulating in the synaptic knobs of all those neurons within your neural pathway that you have been traveling through. So when the action potential arrives now, all that calcium that has been accumulated causes a sudden burst of neurotransmitter by activating these synaptic vesicles to open up and release a large amount of neurotransmitter into the synaptic cleft. This causes an intense excitation in the postsynaptic neuron. An EPSP is created, and this is very strong. It has a high voltage local potential. In this way, you can jog your memory. We have a fancy name for this, and we call this post-tetanic potentiation. And this is a process that takes advantage of calcium accumulation in the synaptic knobs. So even a very short review session following the study session greatly enhances memory encoding. So let's say that you have been very good about your study process. You have been focused during the working memory session. You have reviewed your material many, many times, taking advantage of the tetanic stimulation. Then you have reviewed your material within 3 to 4 hours to take advantage of all that calcium that has accumulated. Now, all of this will go to waste if you don't get any sleep. During your waking hours, all this learning has taken place within the neurons of the hippocampus. So when you go to sleep, the hippocampus teaches the cerebral cortex all that it has learned during the day. In fact, it is not all that it has learned, but it streamlines the most important concepts and teaches it to the cerebral cortex. This is a very important process in learning, and this happens only when you sleep, and we call it memory consolidation. Now let's take a look at how long-term memory is established. Long-term memory can be enhanced by retrieval practice, which is accomplished by repeated quizzing and testing. Here we are in the learning neurons of the hippocampus. The action potential has arrived at the synaptic knob. This causes voltage-gated calcium channels to open and calcium rushes in. It causes exocytosis of the synaptic vesicles that release glutamate. Glutamate then binds to its receptors on the postsynaptic neuron. Notice that there are two types of glutamate receptors. Those that are shown in white are ligand-gated sodium channels, and those that are shown in blue are ligand-gated calcium channels. Both of these channels open, allowing both sodium and calcium to enter the postsynaptic neuron. Since they bring positive charges in, the postsynaptic neuron becomes depolarized. The excited neuron, postsynaptic neuron, responds by adding more glutamate receptors to its membrane. In this way, many more channels open and more ions enter the postsynaptic neuron, continuing the depolarization of the postsynaptic neuron. The postsynaptic neuron does one other thing. It also releases nitric oxide. Nitric oxide is a gas that can easily diffuse out of the postsynaptic neuron. It goes back to the presynaptic neuron, enters the presynaptic neuron, and causes the synaptic vesicles to become activated and release much more glutamate. This continues in a positive feedback cycle until the long-term memory is established. One very important aspect of long-term memory is that it has the ability to physically change the structure of the dendrite in the postsynaptic neuron. We have just seen that the postsynaptic neuron has added glutamate receptors to its membrane. So in this way, long-term memory can profoundly change the morphological structure of a synapse. The last stage in learning is myelination. Myelination is important if you want to master a topic, a concept, or a skill. So the trick is to master something is to retrieve the information as quickly as possible. So you should be able to retrieve information quickly and also make quick connections. So one way to do that would be to increase the size of the myelin sheath. As we remember, when a neuron is myelinated, information jumps from one node to the next, and so the action potentials move much faster. So the secret to myelination is slow learning. So it's the opposite. If you want something to move fast, you should do slow learning so that you allow time for this myelin sheath to physically increase in size.